and today's topic for our class is electric dipole and field due to electric dipole at its axis as well as equatorial plane. So what is an electric dipole? First of all, we need to understand that. Electric dipole. Electric dipole. Okay, so electric dipole is simply two charges, one positive and one negative of equal magnitude separated by a distance 2a. For example, I have this charge plus q and I have this charge minus q, which is separated by a distance named or say 2a distance. This configuration is known as an electric dipole. So the magnitude of the electric dipole, it is denoted by P. It is denoted by P and it is a vector quantity. Okay, so P, the magnitude of P is equal to Q times 2A. Charge multiplied by the distance between the charges is the magnitude of this P. What about the direction? Direction is minus Q to plus Q. This is the direction of P. So if I denote this as P, I am not wrong. So from negative to positive, this is the direction of P. So let's find out the electric field due to an electric dipole. So as we all know, when we have to find out electric field due to a system of charges, we use the superposition principle. We simply find out the field due to one charge and then find out the field due to second charge and add both the fields to find out the net field at a given point. So for example, if I want to find out the field at point P, this is a point P and I want to find out the field at this point. This point is at a distance r from the center of the dipole. This point is at a distance r from the center of the dipole. Okay, so this point is on the axis of this dipole. So when I'm taking a point which is on the line joining the two charges, then that point is on the axis of that dipole. So we are finding out now electric field on the axial point due to a dipole. We are finding out electric field due to on an axial point due to a dipole. Okay, so I am denoting it as EP. Now, as the superposition principle says, EP will be equal to E due to plus Q plus E due to minus Q. When I add these two together, I will get the net electric field at point P. Okay, so what is E plus Q? E plus Q, what is E plus Q? Q over 4 pi epsilon naught R. What is the value of E? E is equal to Q over 4 pi epsilon naught R. So I am using this result here. So what is plus Q? Q over 4 pi epsilon naught. What is the distance of point P from charge Q? What is the distance of point P from charge plus Q? So when you see this is the center, this distance becomes A. And this from the center to the point P, the distance is R. So this means this distance is nothing but R minus A. This is squared. So it becomes R minus A whole squared. So E due to plus Q is Q over 4 pi epsilon naught R minus A ka A whole square. So what is the direction of this field at P? So it is along the direction P. Why? Because the electric field lines because of Q will emerge out of Q, go towards P from the Q. So it is in the same direction as P. So I will add them up. I will just write P vector over here, unit vector P. So it is in the same direction. Now I can write vector here also. So E due to plus Q vector is given as this. Similarly, E due to minus q, if I have to find out, it will be minus q over 4 pi epsilon naught. What is the distance of point P from minus q? 2a plus r minus a. You can say r plus a. This distance is a, so it becomes r plus a. The distance of point P from minus q is r plus a. So I will write it here, r plus a whole square. And the direction, again, this negative sign says it is in the opposite direction of P. It is in the opposite direction of P. P is in this direction. Electric field at P due to minus q is in opposite direction, in that direction. So these are the two quantities. Now I will add them vectorically to get my EP. So how to add them vectorically? Let's see. So E at P will be equal to E plus Q, that is Q over 4 pi epsilon naught R minus A whole square minus Q over 4 pi epsilon naught R plus A whole square. And this entire thing is with unit vector P. It's in the same direction as P. Okay, so let's find out, let's calculate this now. So moving forward, what we will do is we will add them up. How we are going to add them up? Q over 4 pi epsilon comes out, inside remains R minus A whole square minus 1 by R plus A whole square P vector. So it turns out to be Q by 4 pi epsilon. This is R minus A into R plus A whole square. 1 R plus A whole square minus R minus A whole square. P vector. So it turns out Q over 4 pi epsilon R square plus A square plus 2AR minus R square plus A square minus 2AR over R square minus A square power 2. Okay, so moving ahead, Q over 4 pi epsilon naught times of 4AR over R square minus A square power 2. So when when R is much greater than A, when R is much greater than A, what happens to this expression? Can anyone guess what happens to this expression when R is much greater than A? What is the meaning of this, that R is much greater than A? The meaning of this is that this distance as compared to A, which is the distance between the two charges, is very large. So a dipole exists in small molecules. So whenever we want to find out the field due to electric dipole, we have to ignore the distance between the two molecules. So we will be doing that when we will be taking r much greater than a. So it will turn out to be q over 4 pi epsilon naught times of 4ar over r, because this a square will be even smaller than r square. So this a square will get neglected. R square power 2 p vector. So this implies q over 4 pi epsilon naught 4ar over r power 4 p vector, which is equal to, this r gets cancelled, here comes power 3. So this becomes 2 times of 2a cube over 4 pi epsilon naught r cube times of p vector, which we can write it as, because 2a times of q is nothing but the magnitude of the p, magnitude of the dipole. So I will write it down 2p over 4 pi epsilon naught r cube. Okay, so this is what E at P due to a dipole. So here comes the result. The result says the electric field due to a dipole at a point P on the axis of the dipole is 2 times the dipole moment is proportional to the distance cube. The cube of the distance of the point P from the center of the dipole is proportional to the cube of the distance, inversely proportional to the cube of the distance. Okay, so this is it. This is the potential, the electric field due to a dipole at its axis. In the next video, we will discuss about the potential due to a dipole on its equatorial plane. Thank you.